So just as our sun, before it began nuclear fusion in its core, was called a proto-sun, so also stars, before they have nuclear fusion going on in their cores, are called protostars. So when a star in its core is converting hydrogen to helium, like our sun, we call that stage of its life a main sequence. That star isn't what we say, it's its main sequence stage of its life. So we kind of looked on the previous slides how we go from basically a nebula ultimately to a dense core to a protostar to a star. And remember then, when a star turns on, and I think this happens pretty quickly, when a star ultimately turns on, then it has this energy in its core, and so it now finally has a very firm outward pressure to combat the pressure of gravity inward. And it takes about 30 million years for this process in a star that's about the mass of the sun. So just to kind of summarize, here we have this could be this could be a lumpy part within a molecular cloud, but we have gravity going ahead and creating a warmer spot that ultimately can heat up to become a star. We definitely have contraction going on, and that needs to get sufficiently hot and dense in the core in order to sustain what we call nuclear fusion. When the star turns on, we have nuclear fusion in the core, then that is finally balancing kind of this inward force of gravity. So it's in a state of what we call equilibrium. So we talked about clusters of stars can be born at the same time, and aren't these just a beautiful set of stars? Different colors, different luminosities, different masses. And we talked in the previous chapter about HR diagrams. So here's an HR diagram. Remember the important band of stars from the upper left to the lower right, called the main sequence stars. So we talked about a mass luminosity relationship with regard to main sequence, the stars that are on the main sequence stage, and we said that these luminous stars up here in the upper left are most massive, and they're relatively rare. And then these down here on the main sequence have a relatively low mass, and as it turns out, they are very common. And the reason when we look up in the nighttime sky, actually, we have a hard time picking these out or even necessarily seeing them is because they're dim. These low luminosity, low mass main sequence stars, even though they're very common. So there are some limits on the mass that a star can be, and I mentioned this in the previous chapter. I mentioned an upper limit of about 100 solar masses, and the reason for this is if it's too massive, remember that the fusion rate in the core of the star is directly related to its mass, and the more mass a star has, then the higher that fusion rate. So basically what we have, if a star is a protostar before it has nuclear fusion in its core, if it's too large, then when it does turn on, that fusion rate is just too great, and it kind of settles in ultimately to a lower mass probably. So there are stars out there that are more massive than 100 solar masses, but they're very rare and they're not real stable. So the lower limit on a star's mass we said was 0.08 solar masses, and now I kind of want to describe why that is in terms of a star arriving at the main sequence. Why do these lower mass stars not go ahead and these stars that are less massive than 0.08 solar masses, why can't they go ahead and begin nuclear fusion in their cores? And there's a little bit of a quandary there. Even with that low mass of a material, 0.08 solar masses, which is still pretty hefty, the thermal pressure actually shouldn't stop it from contracting enough to get the conditions required for nuclear fusion in its core. So there's something else that must stop that contraction in these light objects. In order to kind of describe what that is, what stops contraction in these light wannabe stars, need to kind of revisit the overall structure of an atom. Remember we talked earlier that atoms are made up of nuclei in their center with protons and neutrons in the nucleus, and then the electrons exist in a cloud outside the nucleus. And we're going to see that with these, with stars, low mass stars, it's actually the electrons that provide the stop, I'm not contracting anymore sort of thing. And according to quantum mechanics, electrons, just like it says down here, no two electrons can exist in the same state at the same place. So just to kind of point out or remind you what we mean by thermal pressure. So thermal pressure is the hotter an object, you can kind of see this gas in a balloon up here. There's cold gas here at the left and hot gas here at the right. And notice that this gas, as it heats up, the gas inside the balloon is going faster and faster. It's got more energy, kinetic energy, and it's got more pressure, and so it's making that balloon expand. And so there is definitely this thermal pressure that can go against the potential contraction of a star. But that's not what stops the contraction of these low mass objects. What stops the contraction of these low mass objects is the degeneracy, electron degeneracy. So it looks something like this. If these chairs are locations that the electrons can exist in, and these people are electrons, okay, what happens ultimately at some point in these low mass objects is that notice there's fewer and fewer chairs, but there's still the same number of people. People represent electrons. So at some point, people can't sit on each other's laps. So eventually then it's this sort of, I'm not going any further, I cannot be squished anymore, that stops the contraction of these low mass objects to become that wannabe stars. So we're going to be talking more about degeneracy pressure later on when we talk about white dwarfs and neutron stars and black holes. But this would be electron degeneracy pressure is winning out here over gravity. Bottom line, what I want you to know at this point is that we have these stars, these wannabe stars that are formed in these molecular clouds along with these other objects that will become stars. And if they're less massive than 0.08 solar masses, that's 8% of the mass of our sun, then they just won't get off the ground. And their cores won't ever reach the temperature required to sustain nuclear fusion. These objects are called brown dwarfs. I think it's funny because brown dwarfs are not related to white dwarfs, and then we have a red dwarf, and we also have, I guess now, a black dwarf. So, and of course we have a dwarf planet. We use the word dwarf a lot in astronomy. So, brown dwarfs are failed stars, but it's not to say that they won't, that we can't know that they're out there. In kind of the early on contraction process that never succeeds to increase the temperature in the core sufficient to sustain nuclear fusion, they still get warm, and so we can actually we can see that heat coming from these objects. But like this last point says, over time, these brown dwarfs will just kind of cool off and be little orbs of failed stars. So this is a region in the this is a star-forming region in Orion, this nebula, numbers and numerous sorts of stars being formed. But these circles here are actually indicating where these brown dwarfs are. So these would be the failed stars. So just to kind of remind you, and I set the criteria earlier at 100 solar masses, but this says 300 solar masses. I would stick with 100 solar masses. 100 solar masses or larger, the star generally is too massive and needs to kind of settle down to something lighter. And if it's too light, less than 0.08 solar masses, it's not going to become a star because it will never get warm enough in its core.